Now, let us answer the question. How big can a drop be, this drop of charged liquid? And how long can this drop exist? There is surface tension in the drop, which tends to compress the drop and make it spherical, and there are Coulomb forces that try to break it, since this nucleus is positively charged. As a result, the surface of the drop, the size of the drop, depends on the opposition of these two forces. One is proportional to a to the power of 2/3. This is on the surface, and the other is proportional to z squared over r, and r is z squared of a to the power of 1/3. So the ratio of these forces is nothing more than z squared over a, the square of the charge divided by the mass. This will be the measure of the facility of the nucleus. Here is the critical point. Once the process has run its course and everything is divided, z squared over a will be equal to a certain value, brackets z squared over a, close the bracket, subscript crit. And according to Bohr's theory, this value equals 50. And at 50, this barrier is 0. This is the moment when the division time is 10 to the power of minus 19 seconds. A more precise expression is written here, which takes into account that not only protons are in the nucleus, but also neutrons. So a correction for neutrons has been made. And then the facility of the nucleus, which we denote by x, is z squared over a by 50.883, plus this correction term, which contains the number of neutrons. So, spontaneous division. Uranium-238 has a z squared over a of 35.6. Its half-life is 10 to the power of 16 years. A superheavy element, according to the droplet model, in which the barrier is 0 and corresponds to brackets z squared over a closed brackets subscript crit, experimentally minus 46.2, and here the time is 10 to the power of minus 19 seconds. Here is superheavy uranium, 42 orders of magnitude difference in stability. According to Bohr and Wheeler, this will be applicable to the second group of elements above 100. Elements with Z larger than 100 cannot exist if the drip model is correct. Here is spontaneous division. Here we draw a barrier. It's pretty big for lead. The height of this barrier is about 13 megaelectron volt. For uranium, this is 6 megaelectron volt, as we have seen. If we come to the 98th element, it is about 3 megaelectron volt. The 108th has a zero barrier, nothing at all. And what did the experiment show? After 1939, there was a war, and then the scientific community began to build reactors, and in these reactors, elements heavier than uranium were obtained, such as plutonium, curium, californium, fermium, and so forth. Look at this sharp decline. And this is the order. From uranium element 92 to the 100 element, a drop of almost 20 orders of magnitude. It is easy to see that if this continues in the same way, then the 106 or 108th element will have such a short lifespan that it makes no sense to even talk about an atom, because the nucleus will decay before orbital electrons will appear around it. This is the limit of the material world. Now let us look at our world. Here it is. Here are the stable elements, little black nuclei. Here are the red ones, that are long-living ones. As we move away from the line of stability, the lifespan decreases. Then it all ends with lead and bismuth. There are no stable elements beyond bismuth and lead. Here they are short-lived, as you can see. But as soon as we go further to the region of uranium and thorium here, long-living elements appear, and uranium, although it decays and albeit radioactive, we see how it decays. Its half-life is 4.5 billion years, which is approximately equal to the age of the Earth. This quality shows that it is radioactive. and we see how it decays. However, it is enough to add 10 protons to uranium and go from the 92nd to the 102nd element, and the half-life becomes 2 seconds in relation to alpha decay. And if you look at spontaneous fission, then the half-life becomes about a second. That is, the movement from here to here changed the stability of the nucleus relative to spontaneous fission by 23 orders of magnitude. Moving further, there is a sea of instability, and even further on, there are no nuclei. There can't be. Whether there are or aren't, it means that if we move only a small distance, then we will come to a situation where the lifetime of the nucleus will be 10 to the power of minus 14 seconds. At this point, there won't be time to form electrons around this nucleus. Well, here is this scale which shows us approximately what it looks like. Half-lives are here. Red means 1,000,000 years, green means an hour, and when we talk about blue, it means microseconds.